All right, video time. Bum, 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 bum. Video time. Let's do this. I wish I had one of those like intros where you could like those cool YouTubers do, where they put all the cool pictures and the whatevers, but I'm not that cool. Ah well. So today, one of my favorite lessons is on related rates. In the next couple slides, we'll talk about what a related rate problem means. I got a warm up right here, practicing particles in motion, so average or so velocity and acceleration and position, those types of problems here. All right, and we'll do this in class together, but for now you can try it on your own. So let's move on. Let's move on. There we go. Oh man, gateway number one. Oh man, we would have had our first derivative gateway today. Oh, y'all would have loved it too. Oh well, I guess for a different day. Okie doke. So let's talk about what a related rate problem means. And I got a bunch of problems we're going to be practicing today. I'm going to try to get as many of them as I can done in 30 minutes, and we'll finish the rest of them in class. So a related rate problem is an application in which one or more rates of change are given, and you are asked to find the rate of change of some other related quantity. So normally the problems we've been dealing with, we just have one rate of change, and that's the rate at which x is changing. Now we're having multiple rates of change given in a problem. And you'll see all the different contexts of how that can happen. And we're going to try to come up with some type of equation or some type of problem that can help us solve this out. Okay, so here we got a list of procedures to help us solve related rate problems, and the steps are listed as above or as below. First of all, read the problem carefully. I know that seems like a silly step there to put in there, but I promise you, sometimes these word problems are going to be long with a lot of information and a lot of confusing words, but they're not terrible problems. You just got to break them down and figure out what they're asking. If I'm able to, I always try to illustrate the problem. These are going to seem kind of similar to when you were doing like um, drawing pictures for maybe um, angle of elevation and depression. It's going to be similar to that and how you draw your pictures. All right. Um, yes, you're going to try if possible, and then this is for any time t. Okay, and we'll discuss more of that here in a minute. All right, whenever you draw your picture and you read through your problem, you want to identify and label on your picture all the fixed quantities with constants and all the quantities that's going to vary with times with variables. And again, you'll see all this in practice here in a second. So any rate of change given in the problem are the rates of change of these variables, and the unknown rate will be the rate of change of one of these variables that we're going to be solving. Okay, so steps 1 through 3 is all about breaking down the problem and labeling everything that you know. Now, step 4 is where the math starts to begin. Okay, we're going to have to come up with our own equation. We're going to have to find an equation that relates everything together, the constants, the variables, everything. And sometimes it's going to be obvious, sometimes we'll have to think a little bit about it. Okay, now once we find that equation, we're going to differentiate it, usually implicitly, but it's always with respect to time t. So my variable here, my variable will usually be t. Okay, everything else would be done implicitly. And then we're going to substitute all known quantities and everything that we can in number 5 and solve the unknown rate. Okay, so keep these in mind. Maybe keep these, as you're trying these problems, keep these in mind and try to go through them as you can. Let's look at one problem together. All right, this is a very common problem that you'll see with related rates. I see this problem show up all the time. It says a ladder 13 feet tall is leaning against the side of a building. If the bottom of the ladder slides away from the wall at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 5 feet from the wall? Okay, usually in class, I'd have something leaning up against the wall. I think I usually take like a broom or something, and I kick out the bottom from beneath it. So I want you to try to picture that right now. There's a ladder leaning up against the wall. Picture the ladder slipping out and falling. Okay, so let's kind of draw this out. I'm going to draw my ladder here. a nice little ladder. It's leaning up against the wall, and here's the ground. Okay. Now what's happening is the ladder's falling. So what's going on is the ladder's feet is shooting to the left here, and the top of the ladder is shooting down. Can you picture that happening? The ladder falling, it's shooting out as the top of the ladder is moving down. Now that is one fluid motion. It is all happening. I mean, it's in real time, right? The ladder's falling, all that good stuff. Well, what we're doing with related rates problem is it's almost like we're taking a picture. We're taking a snapshot of this ladder falling. And we're looking at like one specific time while this ladder is falling. In this exact problem, we're looking at this ladder right at the snapshot when the ladder is 5 feet from the wall, when the base of the ladder, or the bottom of the ladder is 5 feet from the wall. So it's like the ladder's falling, we take a picture of it when it's 5 feet from the wall, and we're going to label it accordingly. So as it's moving out, we're right here at 5 feet. And because this is a horizontal distance, I'm going to label this as x is 5 feet. Okay. I also know that the ladder is 13 feet. Okay. Now, it's asking how fast is the ladder sliding down from the wall. It doesn't tell me where the actual position of the ladder is on the wall. Like, I don't know this. We'll call that y, because we don't know what that is. So we'll just call it y for vertical distance. And because we use x for the horizontal, y for the vertical, we'll call this one z. We'll call that z for the horizontal distance. Or not the horizontal distance, the diagonal distance. Okay? All right. So what we just did is we labeled all of the distances, all of the distances that we can on this triangle. Oh, I already gave it away. Well, on this ladder on the wall. Okay. Now, with whatever variable that you write down, we also want to write the rate at which that variable is changing. So that's something else I like to label. I like to label all the variables and all of the rates of change. So for instance, dx over dt, all right, that is the rate at which the x value is changing with respect to time t. And in this case, it tells me is 2 feet per second. It says how fast is the top of the ladder sliding down the wall. So it's asking us to find dy over dt. I don't know what that is. Now again, every problem we've done before, we've taken the derivative with respect to x. Now we're taking the derivative with respect to time t. So anytime I take the derivative of any variable other than t, I'm doing so implicitly. So if I take the derivative of x, it's dx over dt. If I take the derivative of y, it's dy over dt. Okay. And lastly, dz over dt, the rate at which z is changing. I want you to think about that. The ladder is 13 feet. Is the length of the ladder ever changing? No. So thus, the rate at which z is changing is 0. It never changes. That is a constant. All right. If we have a rate being 0, that means this z right here is a constant. It is not changing with respect to time t. Okay. So then the question we ask ourselves, okay, so we got everything labeled. We got the variables labeled and the rates at which the variables are changing. Now, always kind of underline or figure out what the question is asking you to find. It says, how fast is the top of the ladder sliding down the wall? That is the rate at which y is changing. If that's what it's asking me to find, I need to know all of the other variables. Okay. Well, how can I figure out the other one that's missing? I'm missing y. How do I figure that out? Well, I'm sure I've already kind of noticed it here. This is a right triangle. So we could just do Pythagorean theorem. We could say 13 squared equals 5 squared plus y squared. And doing some quick math there, I think it's 12, but I'm not 100% sure. 13 squared minus 5 squared. Yeah, it's 12. So y equals 12. Okay. All right. Now, we got all the missing sides and everything. The next question, let's go back to these notes here. We read the problem carefully, we illustrated it, and we identified all the variables. So in steps 1 through 3, we set the problem up. Now, step 4 is to say, it says to find an equation that relates everything together. Well, I've kind of given that away already, but once I label everything, how do I relate X, Y, and Z together? What is an equation that could relate those together? And y'all probably kind of already saw it right here, the Pythagorean theorem. So I'm going to write that down. I'm going to write x squared plus y squared equals z squared. So step 4 was to identify all the, an equation. Step 5 was to then differentiate it with respect to time t. So I'm going to take the derivative of all 3 of these variables with respect to time t. So for instance, x squared would be 2x dx over dt. That's the derivative of x with respect to time t. Plus 2y is the derivative of 2y, but again, it's with respect to t. And z is going to be 2z dz over dt. Okay. And then all we got to do is plug in everything but what we're looking for, and we got the answer. Okay, so here's the good thing. And some teachers will even say, like, you know what, z squared is a constant. You don't even need to plug in the variable z because it's always a constant. So what I mean is like, for instance, if I plug in dz over dt, that's just equal to 0, which crosses this whole thing out. So this is actually just equal to 0. All right. I mean, you can do 2 times 13 times 0, but it is just equal to 0. Here we got 2 times 5 times 2 for dx over dt. Here we got 2 times my y value is 12, and my dy over d value is the variable I'm looking for, or the answer I'm looking for. And notice how we got everything else filled out. Okay, so let's simplify it. 2 times 5 times 2, what's that? 20. So I'm going to subtract that to the other side. So, and this is 24. So how about 24 dy over dt equals negative 20? I'm going to divide those, and I get dy over dt equals negative 20 over 24, which we'll just reduce that to divide by 4. How about negative 5 over 6? And the units of measurement in this case are what? Feet per second. So there you have it. So the rate at which the ladder is sliding down the wall is negative 5.6 feet per second. And it should make sense that it's negative because the distance of the ladder to the ground is decreasing. It's getting smaller. It's going down. So your rate is negative. Now, I know it seems like a lot of stuff, but it's going to become very procedural. I mean, all I do every single time is I draw a picture, I create an equation, and I solve. Really, those are the 3 basic things: picture, equation, solve. Let's try another one. 13 minutes. Yeah, let's try another one. I want to see which ones I want to do in class. Yeah, I may do 1 or 2. 1, maybe 2 more. Okay. It says an observer 300 meters from the launch pad of a rocket watches it ascend vertically at 60 meters per second. Find the rate of change of the distance between the rocket and the observer when the rocket is 400 meters high. Okay, long problem. Let's read it carefully. Let's draw a picture. An observer 300 meters from a launch pad. Let's start there. Here's my observer. Hey, how you doing? I'm an observer. He is 300 meters from the base of the launch pad. Here's my launch pad. Now, he's watching as a rocket ascends vertically at 60 meters per second. So, okay, we're watching it. Let's say the snapshot that we take a picture of is right here. Here's my rocket. I'm a rocket. That's the fire coming out. That's the fire. Okay, that's the rocket. Anyway, currently this rocket, let's draw that little line right here. Currently the rocket is ascending vertically, so my Y value is increasing at 60 meters per second. All right, so that's something interesting. It says find the rate of change of the distance between the rocket and the observer when the rocket is 400 meters high. So there you go. Right now, the snapshot that we're looking at, and I should have said this is dy over dz, I apologize. The snapshot that we're looking at is y equals 400 meters. So as this thing's ascending up vertically, we take a snapshot of it at 400 meters. The question is asking us to find is the distance between the two. It wants to know the rate at which that distance is changing. So it's curious about, and sometimes I even label this at the very beginning, it's asking me to find dz over dt. Circle it if you need to. This is what we're looking for. So I need to know everything else. So for instance, like I know that x is equal to 300 and y is equal to 400. I know that dy over dz is equal to 60. I need to figure out what dx over dt is, and that is a t. I don't know why I said z. It's a t. All right, what's the rate at which x is changing? Well, if the vertical, like if it's only changing in the vertical direction, going up and down, it's not changing in the horizontal distance at all. So this is 0, meaning this number right here, 300, is a constant. The only other number I need is z here. And again, I'm sure you can tell this is a right triangle, so we can figure out at this snapshot what the current distance is between the observer and the rocket. I could do 300 squared plus 400 squared equals z squared. And if you do a little bit of math with the Pythagorean theorem, you'll get 500. Okay, so we got everything that we need. We got all the variables accounted for, and we got all of the rates of change of those variables accounted for. The only thing we're missing is what we're asked to find. Now, you have to, once we illustrate everything and label everything, we have to come up with an equation that relates everything. And just like before, I'm sure you're recognizing an equation that's going to relate all the variables, x, y, and z together is, again, the Pythagorean theorem. So we got x squared plus y squared equals, where's the other one at? Oh yeah, z squared. What am I doing? Okay, let's take the derivative. So 2x dx over dt plus 2y dy over dt, and lastly 2z dz over dt. Okay. All right, let's plug in everything we know. Now, again, remember the constant is x here. So, like, if I plug 0 in for x, it just goes away. And that means if x is a constant, that means at the very beginning here, I didn't even have to plug in x. I could have just plugged in 300, and the derivative of the constant just goes to 0 anyway. So, if you have a constant for a variable, you don't have to label it as its own variable. You can just say, hey, that's a number, it's going to go to 0. Plus 2, okay, y was what, 400? And dy over dt was 60 equals 2 times, now z was 500, and I'm looking for dz over dt. Now, a question I want you to ask yourself is the answer going to be positive or negative? That's always a good thing to help you make sure you're on the right track. As this rocket's increasing, is the distance between them also increasing or is it decreasing? And I think it's pretty obvious that it's going to be increasing. So your final answer better be positive. Okay, let's simplify it. So what's that? I don't know. All I gotta do is divide by 1,000. So let's say 800 times 60 is that, God, I can't math right now. 4,800? Is that right? 4,800, 48,000 divided by 1,000? There we go. Jeez Louise, sometimes I can't math. All right, now if I divide that out, it looks like it's just going to be 48. Is it meters per second? It is meters per second. And notice how that answer is positive. So we are on the right track. Makes sense to me. Very nice. Okay, so again, we drew a picture and labeled it. We wrote an equation that relates everything, and then we just took the derivative and plugged stuff in. So it's not the most terrible thing in the world. Let's try one more. Okay, last one. And I wanted to give you something a little bit different than the previous two problems. Let's think about it. It says a spherical ball has its diameter increasing at 2 inches per second. How fast is the volume changing when the radius is 10 inches? Now, something I want to clarify here. Look at the rate that's given to you. The diameter is increasing at 2 inches per second. So we'll call this variable maybe capital D. And if they give you a specific variable and they're telling you the rate of change of that variable, I don't think it matters so much in this problem, but it will in the future. Always make sure, like here, we're given D, call it capital D over dt. We're given the rate at which the diameter is changing. And it wants to know how fast the volume is changing when the radius is 10 inches. So if the rate of change is in terms of the diameter, then maybe we should also write our variable in terms of diameter. So if you notice, like right here, we're given that a radius is 10 inches. Let's make sure to label that as diameter being 20 inches, right? Diameter is just double the radius. I think that's going to help, okay? So it's giving us the diameter at a given moment of time, and it's giving us the rate at which the diameter is changing. But it's curious about how fast the volume is changing. We'll call that V. So if you notice, my two variables here are volume and diameter. Now, is there a way to relate volume to diameter? Well, absolutely there is. It's talking about a spherical ball, so it's just the volume for a spherical ball. That's the equation we're going to use. You want to label the picture. There's not much to label. The snapshot we're looking at is 20 inches for the diameter. And we also know that the rate at which that's changing is equal to 2, positive 2. And what we're curious about is the volume. Okay, the volume and how fast it is going to be dV over dt. So if those are my two variables, I need to know everything but dV over dt. All right. So for those that don't know, the volume for a derivative, volume for a sphere is 4/3 pi r cubed. And yes, you need to commit that to memory because I have seen this problem pop up multiple times. All right. Now, the only thing is that in this particular problem, the variables are, what's another way that we can write this equation in terms of D and V? Well, that's kind of, I want an equation that relates the diameter to volume, but just remember that the radius is nothing more than the diameter divided by 2. I said capital D, I'm sorry. So why don't we just change this as volume equals 4/3 pi, and instead of r, we'll just call that D over 2 cubed. Okay? So there you go. Now let's keep going. Let's go ahead and take the derivative, see what we're dealing with here. So we got derivative of v is dv over dt. equals. Now, if I want to take the derivative of this, notice that the only variable out of all of this is just the letter D. So let's kind of simplify this just a little bit to help me do that. This is the same thing as, all right, notice if I were to distribute the power for D over 2. Let's make this look a little bit nicer for us. That is going to be D to the third power. But we also have 1/2 raised to the third power. And 1/2 raised to the third power is 1/8. And then 1/8 times 4/3 is 4 over 24 pi. Okay? All I did was just simplify everything out. And I can simplify it even a little bit further here too. I can say that 4 over 24 is just 1/6. So this is the same thing as pi over 6 d to the third. So all I did was just simplify out the volume equation just a little bit so we can take the derivative a little bit nicer. And it's just power rule now. So boom. So pi 6 times 3 is going to be 3 pi over 6, or pi over 2 d. And then the power of 3 goes down to a power of 2. And then remember, dd over dt. Okay. And what we're asked to find is dv over dt. And notice how nowhere in the problem is it required for me to actually know what the volume is at this time. So I'm just going to plug in everything else that I know. This is going to be pi over 2. I know the diameter at this given time is 20. And it tells me that dd over dt is always 2. So what this equals is, see, 20 times 20 is 400, times 2 is 800, divided by 2 is 400 pi. I think it's inches per second, maybe. Yeah. So the rate at which my volume is changing, and actually, this is talking about volume. I apologize. This is dv over dt. So volume is actually inches cubed. Inches cubed per second. It's the rate at which the volume is changing. So there you go. All right, cool. So, all right, let's kind of break this problem down real quick, and I'll end it here. What we did is we kind of labeled the picture here. It wasn't the most helpful picture like the triangle problems were, but we labeled it. And the most important thing is we were trying to come up with an equation that related V and D together. Okay, so we know that volume is 4/3 pi r cubed, and I just went ahead and rewrote that r as d over 2. And when I had all of this information, I just simplified it a little bit, and then took the derivative and plugged in everything I knew. So it's not the craziest thing in the world, but we'll do a couple more problems for practice tomorrow and make sure we're clear on it. And tomorrow's homework is actually going to be a worksheet. So I'll go ahead and post all that right now. All right. Well, appreciate it as usual. You guys are awesome. I hope you'll have a fantastic day, and I will see y'all later. See you on the flip side. Okay, bye.